Section 215.4 of the National Electrical Code permits the use of common neutrals for multiple sets of feeders. This is done to achieve several benefits. Firstly, reduce conductor count. By sharing a common neutral between multiple sets of feeders, the total number of conductors required is reduced, which saves space and costs. Secondly, simplified wiring. Using a common neutral reduces the number of termination points and the complexity of the wiring system. This can reduce labor costs and potential errors. Thirdly, enhanced fault protection. A common neutral provides a return path for all imbalanced loads on the multiple feeders, ensuring proper operation of overcurrent protection devices. The code limits the number of sets of feeders that can share a common neutral to 2 or 3 for specific reasons. Firstly, voltage drop. As the number of feeders connected to a common neutral increases, the voltage drop along the neutral can become excessive, potentially leading to reduced voltage at the load. Secondly, overloading. Sharing a neutral between multiple feeders increases the potential for overloading, as the current from all feeders flows through the common neutral. If 3 sets of 4-wire feeders were connected to a common neutral, there would be consequences. Firstly, excessive neutral current. The neutral would carry the unbalanced current from all 3 sets of feeders, significantly increasing its ampacity and potential for overheating. Secondly, phase to neutral voltage imbalance. The unbalanced loading on the 3 sets of feeders would result in an imbalance in the phase to neutral voltages, which could adversely affect sensitive electronic equipment. Thirdly, overloading of distribution equipment. The increased neutral current would overload main breakers, panel boards, and other distribution equipment, potentially causing damage or electrical fires. In summary, National Electrical Code Section 215.4 permits the use of common neutrals for multiple sets of feeders to reduce conductor count, simplify wiring, and enhance fault protection. However, it limits the number of sets of feeders to 2 or 3 and prohibits the use of a common neutral for 3 sets of 4-wire feeders due to safety concerns and potential electrical hazards. To delve deeper into the reasons why the National Electrical Code, or NEC, allows common neutrals under specific conditions, it's essential to understand the underlying electrical principles and safety considerations. The concept revolves around optimizing the use of conductors while ensuring that the electrical system remains safe and functional. Firstly, let's consider the scenario of multiple sets of 3-wire feeders. In a 3-wire system, you have 2 hot conductors, often referred to as line conductors, and a neutral conductor. Each set of feeders supplies power to a specific load or area. By using a common neutral, you're essentially allowing the return current from multiple sets of feeders to flow through a single neutral conductor. This is permissible because, in a balanced 3-wire system, the neutral conductor only carries the unbalanced current, that is, the difference between the current flowing in the 2 hot conductors. As long as the neutral conductor is adequately sized to handle the maximum potential unbalanced current, it can safely serve multiple sets of feeders. The advantage here is a reduction in the number of conductors required, which translates to lower material costs and reduced installation complexity. Similarly, the NEC allows common neutrals for 2 sets of 4-wire or 5-wire feeders. In these systems, you have 3 hot conductors, a neutral conductor, and optionally a ground conductor. The principle remains the same. The common neutral carries the unbalanced current from the multiple sets of feeders. However, the NEC imposes stricter limitations on the number of sets allowed and the types of feeders that can share a common neutral due to the increased potential for unbalanced loads and harmonic currents in these systems. Now, let's address the question of why the NEC doesn't allow 4 sets of 3-wire feeders to share a common neutral. The primary reason is the increased risk of overloading the neutral conductor. As you add more sets of feeders, the potential for unbalanced current increases, and the neutral conductor may not be able to safely handle the combined load. This can lead to overheating of the neutral conductor, which can damage the insulation and potentially cause a fire. Additionally, overloading the neutral conductor can cause voltage drops, which can negatively affect the performance of equipment connected to the feeders. The NEC is designed to prevent these types of hazards by limiting the number of sets of feeders that can share a common neutral. Finally, let's examine the dire consequences that could occur if 3 sets of 4-wire feeders were connected to a common neutral. In this scenario, the risks are significantly amplified. 4-wire feeders are commonly used to supply three-phase power, which is often used for larger loads and more sensitive equipment. If 3 sets of 4-wire feeders were connected to a common neutral, the potential for imbalanced loads and harmonic currents would be extremely high. This would result in a large current flowing in the neutral conductor, which could easily exceed its ampacity. The consequences of this situation could be severe. The neutral conductor could overheat and fail, leading to a loss of power and potentially causing a fire. The voltage imbalance could damage sensitive electronic equipment, such as computers and control systems. The increased neutral current could also interfere with the operation of ground fault protection devices, which are designed to protect against electrical shocks. For these reasons, the NEC explicitly prohibits the use of a common neutral for 3 sets of 4-wire feeders. The NEC regulations regarding common neutrals are based on sound engineering principles and extensive experience. The goal is to provide a safe and reliable electrical system that protects people and property from electrical hazards. By understanding the reasons behind these regulations, electrical professionals can ensure that their installations comply with the code and provide a safe and efficient power distribution system. Furthermore, it's important to recognize that the NEC is not a static document. It is constantly being updated and revised to reflect changes in technology and industry best practices. Electrical professionals should stay informed about the latest changes to the NEC to ensure that their work is always up to code. In addition to the specific requirements outlined in Section 215.4, there are other sections of the NEC that address the use of common neutrals. These sections provide additional guidance on conductor sizing, overcurrent protection, and grounding requirements. It's essential to consult these sections to ensure that the entire electrical system is designed and installed in accordance with the NEC. In summary, the NEC regulations regarding common neutrals are designed to optimize the use of conductors while ensuring the safety and reliability of the electrical system. By understanding the underlying principles and following the specific requirements of the code, electrical professionals can provide a safe and efficient power distribution system for their clients. It is important to note that the NEC is a minimum standard. In some cases, it may be necessary to exceed the requirements of the code to ensure the safety and reliability of the electrical system. Electrical engineers should use their professional judgment and experience to determine the appropriate level of safety for each installation. The NEC is a complex and comprehensive document, and it's essential for electrical professionals to have a thorough understanding of its requirements. By staying informed about the latest changes to the code and seeking guidance from experienced professionals, electrical professionals can ensure that their work is always up to code and that their installations are safe and reliable. Remember that electrical safety is paramount. Always follow the NEC and other applicable codes and standards when working with electrical systems. If you are not qualified to perform electrical work, hire a licensed electrician. The NEC rules around common neutrals are not arbitrary, they are rooted in practical considerations related to electrical distribution and safety. The code aims to strike a balance between efficient use of materials, particularly copper conductors, and the need to prevent overloading and ensure proper voltage levels. Let's delve deeper into the specific scenarios and the reasoning behind the restrictions. When we talk about feeders with a common neutral, we're referring to multiple sets of conductors originating from a source, such as a panel board or a transformer, that supply power to different loads or areas. The neutral conductor serves as the return path for current from each of these sets of feeders. The NEC permits this arrangement under certain conditions to reduce the overall number of conductors required, which can lead to cost savings and easier installation, especially in large or complex electrical systems. However, there are inherent limitations to this approach. The primary concern is the potential for overloading the neutral conductor. In a balanced 3-wire system, where the loads on each of the 2 hot conductors are equal, the neutral conductor carries very little current, ideally zero. However, in reality, loads are rarely perfectly balanced, and the neutral conductor must carry the difference in current between the 2 hot conductors. This is known as the unbalanced current. As you add more sets of 3-wire feeders sharing a common neutral, the potential for a significant imbalance current increases. If the neutral conductor is not sized appropriately to handle this current, it can overheat, leading to insulation damage and potentially a fire. The NEC limits the number of 3-wire feeders sharing a common neutral to 2 or 3 to mitigate this risk. The limitation on the number of sets of 4-wire or 5-wire feeders sharing a common neutral is even more stringent. This is because 4-wire and 5-wire feeders are typically used in 3-phase systems, which can introduce additional complexities related to unbalanced loads and harmonic currents. In a 3-phase system, the neutral conductor can carry not only the unbalanced current due to unequal loading on the phases, but also harmonic currents generated by nonlinear loads such as electronic devices and fluorescent lighting. Harmonic currents are multiples of the fundamental frequency of the AC power system, typically 60 Hz. These currents can add up in the neutral conductor, even if the loads on the phases appear to be balanced. The NEC prohibits the use of a common neutral for 3 sets of 4-wire feeders because the combined effect of unbalanced loads and harmonic currents could easily overload the neutral conductor, leading to the dire consequences mentioned earlier. These consequences include excessive neutral current, which can cause overheating and insulation failure, phase to neutral voltage imbalance, which can damage sensitive electronic equipment, and overloading of distribution equipment, such as main breakers and panel boards, which can lead to damage or electrical fires. The NEC restrictions on common neutrals are not just about preventing immediate hazards, they are also about ensuring the long-term reliability and performance of the electrical system. Overloading the neutral conductor can degrade its insulation over time, leading to gradual increase in resistance and a further reduction in voltage levels. This can eventually result in equipment malfunction and premature failure. Furthermore, voltage imbalances can negatively affect the efficiency of motors and other electrical equipment, leading to increased energy consumption. The NEC rules are designed to prevent these long-term problems by ensuring that the neutral conductor is always operating within its safe opacity and voltage limits. It's important to note that the NEC is a minimum standard, and in some cases, it may be necessary to go beyond the code requirements to ensure the safety and reliability of the electrical system. For example, in a facility with a large number of nonlinear loads, it may be prudent to use separate neutral conductors for each set of feeders, even if the NEC would allow a common neutral. This can help to reduce the risk of harmonic current overloading and improve the overall performance of the system. Similarly, in critical applications where voltage stability is paramount, it may be necessary to use larger neutral conductors than required by the NEC to minimize voltage drop. The NEC is a living document that is constantly being updated and revised to reflect changes in technology and industry best practices. Electrical engineers and contractors should stay informed about the latest changes to the NEC to ensure that their work is always up to code. They should also use their professional judgment and experience to determine the appropriate level of safety and reliability for each electrical installation. In addition to the specific requirements of Section 215.4, there are other sections of the NEC that address the use of common neutrals. These sections provide guidance on conductor sizing, overcurrent protection, and grounding requirements. It's essential to consult these sections to ensure that the entire electrical system is designed and installed in accordance with the NEC. In summary, the NEC regulations regarding common neutrals are based on a thorough understanding of electrical principles and safety considerations. The code aims to strike a balance between efficient use of materials and the need to prevent overloading and ensure proper voltage levels. By following the NEC rules and using their professional judgment, electrical professionals can provide safe, reliable, and efficient electrical systems for their clients.